Yo, what up, Sci fam? It's your boy Nickel. Today we're gonna learn about orbits, not the gum, but in space orbits. So you see some things that'll be there on our science notebook page. Let's go ahead and jump in and let's define what it means when we say that something is in orbit. You see, it's just simply a curved path of an object that's affected by the gravitational field. Gravitational field of another bigger object. But it is important to know what it means when we say bigger. And this means something that is more massive, because things with more mass end up bending space-time more and more. Something with very little mass has a very little impact on space-time. But if something has a lot of mass, it ends up warping space-time more and more. The gravitational field is that as you get closer to that object that's massive, the gravitational field will increase and it gets bigger and bigger. Just like with a magnet, when you put two magnets close to each other, you might feel the tug of the other magnet, but as you get them closer, you feel it stronger and stronger. So that's what a field is. And in orbit, it's a curved path of an object that's affected by the gravitational field. So let's first look at these three different diagrams below. If I got really close to the object, then it's going to bend the path of my object getting close to it a lot. If I'm not getting this close, it's not going to bend it as much. And if I get even further away, it has less of an impact, but it still will cause there to be a curve in my path. Now, to have a true orbit, you need to have some forward motion. So let's imagine we had this cannon, this purple cannon on the top of the earth here, and we shot a bowling ball out of it. It has that forward motion. As it moves forward, it starts to fall as well. So this bowling ball will fall with that forward motion, and soon it will end up back at the earth, unless that forward motion is great enough that it actually doesn't just land here, but maybe it goes even further and it lands further. More forward motion, it'll fall, but it has that forward motion, so it might land even further. And with enough forward motion, it's going to be launched around, and it would go all the way around the earth because the earth is attracting it, causing it to want to fall near the earth. But if it has enough forward motion, it never falls to the earth. If it has too much forward motion, it just flies straight out from the earth. That's how we send rockets like out to the moon and stuff like that. All right. So if we now dig in a little bit deeper, when we talk about an orbit or a path around an object, this is something known as an orbital period. And this is just the amount of time for one object to complete one orbit around another object. So when one object completely goes around another object. So if we think about like the Earth going once around the sun, what do we call that? Oh yeah, that's right. We call that a year. And that ends up being about 365.2 days if we look at how many days that takes. And that 0.2 there is why we have leap years, because it's a little bit more than 365 days for a year. So every 4 years we have to add a day in our month of February to account for that addition there. We could also look at how the moon orbits around the Earth. And what do we call this? Well, this is actually something, we call it a month. And on average, there's about one moon cycle per month. And the word month is actually derived from moon. It used to be 1 month, but it's a month is what we call it. And that's 27.3 days long. All right, next, let's compare the Earth's gravity to the moon's gravity so that we can kind of analyze orbits a little bit and dig in a little bit to understand a little bit more information about orbits. So if we look at the force of gravity, we need to understand also what the mass of the object is so we can see why the force of gravity is different. You see, the Earth has a mass of about 6 septillion, which is a huge number. It's about 6 times 10 to the 24, and the unit here is kilograms. So 6 septillion kilograms is the mass of the Earth. The moon is not as heavy. It's about 73 times 10 to the 21 kilograms, which is the same as about 73 sextillion kilograms. So it's less mass than the Earth. So when we look at if we look at the Earth, the gravity of the Earth is about 9.8 meters per second squared. the gravity of the moon is about 1.6 meters per second squared. That's a lot less. And when we landed on the moon, we were only able to land on the moon because it had gravity, and we were able to walk on the moon because it has gravity. So it's a complete misnomer that the moon doesn't have gravity. Well, and also that the Earth has gravity because the moon orbits the Earth. And it's interesting too because the moon actually also impacts the Earth because it has its own gravity, but we'll learn about that later on. Now, if we look at both of these places, the Earth or the moon, regardless of where you go, if you were to drop an object or if we put a satellite in orbit around the Earth or around the moon, we need to understand what that really means when we say something is in orbit. So an object that's in orbit, or if we say something's in orbit, basically what that means is that it's just constantly falling without ever hitting the ground. So imagine this bowling ball. Well, it hit the ground, so it wasn't in orbit. Oh, it hit the ground again. It wasn't in orbit. It fell and hit the ground, so again, it wasn't in orbit. And this time it fell, but it just kept going. So therefore, now it's in orbit. It's falling, but it never hits the ground, so it's in orbit. So an object in orbit is constantly falling without ever hitting the ground. So if I just put that bowling ball here, it falls, but it doesn't keep falling because this massive object has a tug to the center of it. So this ball actually ends up getting pulled in by the gravitational field of the massive object. So each time I draw this circle and draw an arrow, this arrow is actually, since there's no up or down in space, it's just constantly falling to the next position. And that's what an orbit is. Now you see that since objects fall at the same rate, meaning that if you were to drop a ping pong ball and a bowling ball here on Earth, they would both fall at the same rate and hit the ground at the same time. Now one would hit the ground harder than the other one, but they fall at the same rate at the same amount of time. The same thing would be true on the moon. They wouldn't fall as fast though because there's not as much gravity on the moon as there is on Earth. But they would still fall at the same rate. They would hit the ground at the same time. Now since objects fall at the same rate, it would actually appear, this is kind of a tricky thing, it would appear as though a person that is falling in an elevator, let's imagine an elevator, actually Einstein imagined this, that there's an elevator that's constantly falling. So imagine there's a person inside of that elevator that's constantly falling and it never hits the ground. Since objects fall at the same rate, it would appear as though a person falling in an elevator shaft would be floating in the elevator. So that elevator is in free fall. The human is in free fall. Let's say we're on Earth, so that's 9.8 meters per second squared, and both of them are falling at the same rate. So therefore, since they're falling at the same rate, it would look like that person could move freely inside of that elevator, and it would look like they're floating. And actually, this is what's happening when you see videos of people on the International Space Station. They look like they're just out here floating when they do their little spacewalks. It looks like people are just floating, but really, the space station is falling and the person is falling at the same rate, so they can easily move around as they please and it looks as though they're floating. So the reason I share this is because it's important to understand that there is no such thing as zero gravity or zero G. You see, because no matter what, anytime you're close to a massive object, there's going to be some gravity. The sun has gravity, and we know that because the Earth is orbiting the sun, so everywhere in between must have gravity. Even out at Neptune, it's orbiting the sun, so everything in between there must have gravity. And to prove that, even the Earth has a moon that's orbiting the Earth, so there must be gravity in between those spaces. And actually, the International Space Station is right here outside the Earth, between the Earth and the moon, so there's no way that there's zero gravity. There is no such thing as zero gravity. Everything is just falling at the same rate, which makes it seem as though some people are in zero gravity. It's just your perspective. Whoa. Go ahead and put your hand on your head, because if your mind is blown, I don't want you to lose any more of those brain cells. But I'll catch you on the next video. See ya!